Um, Guys, we've been looking at errors, and when we round something, we're approximating it. And we said that okay, there's a bit of give above and below our approximation. That's the error that we're talking about. And what that is you see what you're measuring to the nearest. So is it to the nearest 100 or the nearest 1,000 or the nearest 0.1? And then you take half of that unit and you add it on and you take it away. So you add half of that unit to the approximation, and above is your upper bound and below is your lower bound. And that's what we were looking at on Friday. Okay. But what we want to move it into now is using these in calculations, these approximations and calculations. And you'll see hopefully in the examples we've got here. So here's one here. The sports pitch has the dimensions shown, and this is very important. This is the bit that sort of gives away that we're talking about errors, that they're measured to the nearest metre. And we're asked to calculate the maximum minimum areas of the sports pitch. Okay, now we've got the top one is 100 metres, and it's measured to the nearest metre. So what we're going to do here is we're going to add and subtract half of that, or 0.5 of a metre. Okay, so the upper bound for 100 metres is 100 plus half a metre, which is 100.5. And the lower bound is 100 minus half a metre, which is 99.5. Okay. Same sort of thing for the 50 metres. It's measured to the nearest metre, so we're adding half of that. Half of a metre is, well, it's 0.5 of a metre. So the upper bound for the 50, the width is 50.5 metres. And the lower bound is, well, we take away half a metre, so it's 49.5 metres. And that's pretty much what we were asked to do last week. We were just finding upper and lower bounds. But when we go to a calculation, we need to be slightly careful. Because we know that if we want to find the area, it's the length times the breadth. If we want to find the maximum area, then what we want to do is find the biggest value of the length and multiply it by the biggest value of the width, or the breadth, sorry. In other words, I want the upper bound of the length times the upper bound of the width. So we've already worked this out, and that's why it's good to do this at the side. We're going to do 100.5 multiplied by 50.5. And when we get that, so it's just straight into the calculator, and this is one of those few questions that generally you put all the decimal places on your calculator, all the answers. So that's 5,075.25. Again, we're talking area, so in terms of its metres squared. However, if we wanted this to be the minimum area, I want the smallest possible value of the length times the smallest possible value of the breadth. In other words, I want to use the lower bounds. So I'm going to use 99.5 and multiply that by 49.5, the two lower bounds. And when we do that, again, just straight into calculator, we get 4925.25 metres squared. And so the maximum possible area is 5,075.25 metres squared. The minimum possible is 4925.25. I guess the biggest problem people do is they say, oh, the area here must be 100 times 50, which is 5,000. And then they try and find out what the error is and add it on and take it away. But no, it's the 100 metres that has been measured to the nearest metre, so we need to find the upper and lower bounds of it. It's the 50 metres that's been measured to the nearest metre, so what are its upper and lower bounds? And then how does that affect the maximum possible areas? Okay. So So, second type of question here. Same sort of thing. The one important difference, so all 110 marbles shown are identical, apart from their colour, obviously. A marble is taken and measured as 15.6 grams to the nearest tenth of a gram. Find the upper and lower weights for all the marbles. Now again, look, this is to the nearest tenth of a gram. So it's to the nearest 0.1. So to find our upper and lower bounds, we're going to add half of that, 0.05. Okay? So if I want to find the upper bound of a marble, it's 15.6 plus 0.05, which is 15.65. And the lower bound of a marble is 15.6. Take away that, so 15.55. Now, we're asked for the upper and lower bounds for all 110 marbles. Sorry. Just be slightly careful here. There are exactly 110 marbles. That has not been rounded. Okay, there can't be 110.5 or 109.5 marbles. There are exactly 110 marbles. So to find the maximum weight or the maximum mass, we simply need to take 110 and multiply it by the upper bound of one marble. So 15.65 times 110. So that works out for me 1721.5 grams. And for the minimum, the lower bound, then it's 110 times 15.55. Which works out as 1710.5. But the big change in this one is we're only using the upper and lower bounds for the mass of the marbles. We don't use it for the number of marbles. There are exactly 110 marbles. Okay, exactly. That's not an estimation. So moving on then, those are the one with the calculation that everything we use the upper and lower bounds. The second one we use the mixture. In this type of question, it's just a calculation that's been done, and these numbers have all been rounded, and we just need to think carefully about what the maximum value of this calculation and what the minimum value of this calculation is. We're told that all of these have been measured to 1 decimal place. So find the upper and lower bounds for a calculation. So what I'm going to do first is I'm just going to take to one side, just to 9.7, and the upper bound for 9.7 and the lower bounds. Well, if it's been measured to the nearest at 1 decimal place, that's 0.1. So what we're going to do is we're going to add and subtract half of that, 0.05. So that means the upper bound for 9.7 is 9.75 and the lower bound is 9.65. For 4.6, the upper bound is 4.65 and the lower bound is 4.55. And for 2.1 then, the upper bound is 2.15 and the lower bound is 2.05. So that's pretty much everything that we were looking at last week, just the upper and lower bounds of different things. Now, if we're looking for then the upper bound of the whole calculation, the biggest value that this calculation can be, that means I want my fraction basically to be big on top and small on the bottom. Okay, for that value to be as big as possible, the top of the fraction needs to be big and the bottom needs to be small. Well, how do we make the top of that fraction big? Well, I want a big number at the start, so I want the upper bound of the 9.7, and I want to take away from that. Well, I need to take away something small from that to make the top of it as big as possible. So I'm going to take away the lower bound. And on the bottom of this fraction, we want it to be as small as possible, so we're going to use the lower bound. So all that I do then, because I've already worked these out, I'm just going to write these in. 9.75, take away the lower bound of 4.5, which is for 4.6, which is 4.55, and we divide it by 2.05. And so we can put that into our calculator. 9.75 minus 4.55, and that's all divided by 2.05, and that works out as 2.536585. Conversely, if we want to find the smallest value of all of this, well, to get the smallest value, I want the top of the fraction to be small and the bottom of the fraction to be big. Now, how do we do that? Well, to get the top small, I need this to be as small as possible, so I want the lower bound, and I want to take away from that as big a number as possible. So I want to take away the upper bound of 4.6. And the bottom of that fraction needs to be as big as possible, so that's the upper bound. And again, guys, once we've worked our way through that in our heads, maybe written it down like this, you just fill in the values. So LB 9.65, upper bound 4.65, divided by the upper bound of 2.1, 2.15. And again, our calculators can do the rest of the work on that. So 9.65 minus 4.65, all divided by 2.15, and that works out this time as 2.325,582. But again, this was more complicated because there were more things happening in the original equation. So you just need to be very careful. To get this as big as possible, I need the top line to be big and the bottom to be small. How do we do that? Well, I need the top line to be big, this needs to be big, and this needs to be small. And if you can sort of think about it in those terms, then write it in the terms of their upper and lower bounds. And because we've already calculated those, it's just a matter of filling them in and putting it into your calculator. Okay, last one. Again, a cyclist travelled 700 metres along a road and timed at 38.6. The road length to the nearest metre and the stopwatch to the nearest tenth of a second. Find the upper bound and the lower bound for his average speed. Okay, so again, we're talking about 750 metres to the nearest metre. So we're going to add and subtract half a metre. So the upper bound for 750 is 750.5. and the lower bound is 749.5. We've added and subtracted half a metre. For the seconds, this is measured to the nearest tenth of a second, so we're going to add and subtract half of that. So the upper bound is 38.65, and the lower bound is 38.55. Now, again, we know that speed is distance divided by time. So we're using a formula here. To get the upper bound, I need that fraction to be big over small. In other words, I need the upper bound of the distance and divided by the lower bound of the time. So we plug that in. That's 750.5 divided by 38.55. And that works out as 750.5 divided by 38.55. 19.468 seconds. On the other hand, if we want the lower bound for speed, I want my fraction to be as small as possible. So the number on top needs to be small and the number down below needs to be bigger. That means we're using the lower bound for the distance and the upper bound for the speed, for the time. And again, because we've already worked these out, it's just a matter of copying that from above and plugging it into this, and then letting our calculator do the rest. So 749.5 divided by 38.65. Okay, and that works out then as 19.39 198. And that's it. We've done our calculation. We knew that our values were rounded. Okay, and so once we've asked for the upper bound and lower bound, or the maximum value, the minimum value, then we can say, okay, how do we make this as this formula as big as possible? I need the distance to be big and the time to be small. So that's the upper bound over the lower bound. How do I make this value as small as possible? Well, I need the top of the fraction to be small, the bottom to be big. And so we use the upper and lower bounds like so.